Swayam Prabha. Digital India. Educated India.
Last module, we talked about the general problems and challenges that arise in multidimensional data: volume, creation of empty space, concentration of distances, concentration of measures, and lots of other factors that are counterintuitive in smaller dimension. In this module, we are going to concentrate on measure concentration. That means we are going to exclusively talk about measure means probability measure. So, we are going to talk about several bounds that relate to how the probability heap together, how they are going to distribute themselves around certain preferred locations. That is what is called concentration inequalities or concentration of measures. I am going to start with classical bounds. Concentration of measures relates to controlling the tail probability. You remember the last one we saw, as if you consider a fixed distribution such as standard normal, if you increase the dimension of the space in which the distribution is defined, the probability mass escapes from center to the tails. That is migration. If it moves away from that, where does it go? Where does it end up? With respect to Gaussian measures, we showed that while it moves towards the tail, it concentrates itself around the radius of the Gaussian, which is square root of d times sigma. Therefore, if you consider a small annular region around symmetrically placed annular region centered at square root of d, we find a large amount of probability measure is concentrated there. It is not, it does not go to infinity, but it does not stay at 0 either. So, what is counterintuitive in here? When the dimension is 1, the maximum probability lies in between plus 3 and minus 3 in 1D. But here the maximum probability in a Gaussian distribution, you can find them in a small annular space centered around square root of d. The square root of d increases with d. So, that means the probability mass keeps migrating towards the tail as a function of square root of the dimension. So, that is the concentration phenomena we are talking about. So, concentration of measures relate to controlling the tail probability. What is the tail probability? If x is a random variable, if absolute value of x is greater than or equal to t, that is a typical tail probability. X is a random variable, what is the probability that the absolute value of x will be greater than t? In the case of Gaussian, we have already seen when x is standard Gaussian, when t is 3, the probability that the absolute value of the standard Gaussian in 1D greater than or equal to plus or minus, the absolute value of x is greater than 3, that means it lies in between minus 3 and plus 3 is 0.997. That means the tail has very little. But as d becomes larger and larger, the dimension, the probability mass oozes out. It moves away from the center. So, where does it go? and that is what we are interested in studying. A standard way is to use higher order moments of a random variable. I am assuming you are all familiar with basic probability theory. There are two types of moments, central moment, non-central moment. Expected value is the first central moment, variance is called the second central moment. When we talked about Gaussian distribution, we have talked about the third moment, the fourth moment. So, I would like you to go back to the module on Gaussian density to understand the computations of various moments of multivariate Gaussian distribution. The algebra is not trivial. I hope you walk through the details to get the hang of the mathematics that is needed to be able to make these computations. So, now we are going to introduce several ways of trying to compute the tail. The first of such inequality is due to Markov. Markov was a Russian mathematician, probabilist. There is a theory in probability theory called Markov chain, Markov processes. So, he has made many fundamental contributions to the development of probability theory as early as 125, 130 years ago. Then Chebyshev, another Russian mathematician. Chernoff is a statistician in USA. So, Markov inequality depends on the first moment, Chebyshev inequality depends on second moment, Chernoff inequality depends on moment generating function. That is a basic fact that if you give me a probability density function, all the moments can be calculated very easily. Of course, the calculations could be mathematically challenging, but nevertheless it can be done. So, the reverse question is that how many moments should I know in order to be able to decide the distribution? That is a tougher question. In fact, there are very many different types of results. One key result is that you may need to know infinitely many moments in order to be able to reconstruct the distribution from the moments. That is a kind of a worst case scenario. So, probability distribution to moment, moment to distribution, moments, being able to understand the concentration properties based on moments, first moment, second moment, all moments, moment generating function means all moments, I can generate every moment you like. Then the other contributor is called Hofding. There is a new class of processes you can define, it's called sub-Gaussian. Bernstein is another contributor. There is a new class of processes which you can define as sub-exponential. So, first moment, second moment, moment generating function, sub-Gaussian random variable, sub-exponential random variable. These are all the families of ideas we are going to be talking about, and these are needed in the probabilistic analysis of high dimensional system. In a standard course in data science, you probably do not see these things, but when you get more serious about doing high dimensional data analysis, these kinds of tools are absolutely fundamental. So, I am going to start with first called Markov inequality. Let x be a random variable with greater than or equal to 0. It has a finite mean. I do not know anything else about the distribution except that the mean is finite. I can express expected value of x is equal to 0 to infinity x bx dx. For any t finite in between 0 to infinity, I can split the integral from 0 to t and t to infinity. This is a finite number, this is a finite number, both are positive. So, if I drop one of the positive values, it inflates the left hand side, the right hand side becomes less. So, the inflation gives rise to the inequality. Therefore, E of x now is greater than integral t to infinity x px dx, that means the second interval. In this interval, the smallest value that x takes is t. So, I would pick t outside, that further strengthens the inequality. So, this is t times integral t to plus infinity px dx. This quantity is in fact probability that x is greater than or equal to t, probability x is greater than or equal to t. Therefore, this is t times probability x greater than or equal to t. So, e to the x, e of x is greater than or equal to t times probability of x greater than or equal to t. Therefore, if I divide both sides by t, the ratio of ex to t is always greater than probability that x is greater than or equal to t. So, this is a very nice way of talking about the tails. What is the probability of finding x in the interval plus t to infinity? That probability is less than the expected value of x divided by t. So, this inequality is called Markov inequality, and it is the earliest of the inequalities relating to concentration measures. So, that is the equation 1. Now, Chebyshev came along after Markov. He improved this inequality. He said, let x be a random variable with a finite variance. Please understand, mean is the first moment, variance is the second moment. So, knowing the mean, you do not know the variance. There are a lot of unknowns. But knowing the mean and the variance, I know a little bit more about the distribution of the random variable. So, if you give me more information, namely x is a random variable, here he did not assume x is non-negative. So, x is a general scalar random variable with finite variance. Let mu be the mean of x, that means mu is equal to E of x. Now, I want to ask myself the question, the absolute value of x minus mu is greater than or equal to t. So, what does it mean? Here is mu, here is mu plus t, this is mu minus t. So, this is the interval x minus mu absolute value less than or equal to t. The tail is the event absolute value is greater than or equal to t. So, that is a tail probability. This is the tail. So, if absolute value has to be greater, inequalities are preserved by increasing functions. So, x minus mu whole square must be equal is greater than or equal to t squares. Now, x minus mu whole square is a positive random variable, is a centered positive random variable. For this centered positive random variable, that is non-negative, it is 0 only when x is mu, for all other values of x is greater than 0. So, I can apply the Markov inequality to this random variable, to this random event, namely x minus mu whole square is greater than or equal to t square. So, probability that x minus mu whole square is greater than t square. Please recall the Markov inequality. Probability that absolute value of x is greater than t is less than or equal to expected value of x divided by t. So, absolute value of x is replaced by x minus mu. T square, if this is t, this is t, if this is t square, this is t square. So, this is what it is. Now, you know x minus mu whole square is variance. Therefore, the probability that this event happened, namely x minus mu whole square is greater than t square, is less than or equal to variance of x times t square, variance of x times t square. Therefore, we get, so this event is the same as this event, please understand. This event is the same as this event, because the probability measures are preserved under monotonic transformation. If you square a variable, that is monotonic. That means if x1 is less than x2, x1 square is less than x2 square. That is the monotonicity property we are talking about. Therefore, the probability that x will take a value more than mu. The difference between mu and x, absolute value difference is t, is less than or equal to variance of x divided by t square, and this is true for all t greater than or equal to 0. Now, I am going to illustrate this by a simple example, Markov inequality. I am going to be talking about a coin tossing experiment. In a coin tossing experiment, the coin falls head with a probability p is equal to 0.2. I am going to make 20 tosses at a given time. I want to ask myself, what is the bound and the probability that it falls at least 16 times? At least 16 times. And you know, this is a coin tossing is a Bernoulli random variable. So, the expected value of this, if x is equal to 1, if x is equal to 0 with the probability, if x is equal to 1 and x is equal to 0 are two random variables with the probability p and 1 minus p here, the expected value is p, the variance, the expected value of x is equal to p and the variance of x is equal to pq. You should know this from standard probability theory. So, p is 0.2, and if you repeat this 20 times, expected value of the sum of xi, I is equal to 1 to 20 will be equal to 20 times p. The variance of the sum of the sum of xi, variance of the sum of xi, variance of the sum of xi, that is equal to npq, where n is 20. Here, n, I will simply say n, np, npq. So, n is 20, n is 20 and p is 0.2, p is 0.2, 0.2 is 1 over 5, 1 over 5. So, np is equal to 20 by 5, which is equal to 4. So, in 20 tosses, I would like to be able to get 16 head. Please understand, head falls with a smaller probability. The expected value is only 4 heads. So, x wanting to be 16, that means the number is far greater than and 4. So, you can think of this as a tail probability. So, p is 0.2, q is 0.8, h is head is 1, t is 0, expected value of x is 1 over 5, expected value x is equal to 20, this is 4. By Markov inequality, x greater than or equal to 6, 16 is expected value of that by 16, that is equal to 1 by 4. What is the actual probability? The actual probability of, so in a 20 tosses, I want to get at least 16 head. So, I can get 16, 17, 18, 19 and 20. In 20 tosses, the number of ways in which I can have k heads is 20 ck. You all know n ck, that is equal to factorial n divided by factorial k times factorial n minus k, the number of combinations of k out of n, and that distribution is the binomial distribution p to the power of k, q to the power of 20 minus k. I have to compute this sum. This sum is very small. So, what does it mean? The actual probability is very small, but the Markov tells you the probability less than 1/4. That means the Markov inequality is a loose bound. The actual value is much smaller than what the bound gives. So, here is an example that Markov inequality sometimes can be an overestimate of the. Now, consider a second case. X is equal to 0 with a probability p, which is 24 by 25, x is equal to 5 with a probability q 1 minus p. So, the expected value of x is equal to 1 over phi, you can readily see this. So, by Markov x is greater than or equal to phi is less than EFX less than EFX divided by phi, which is equal to 1 over 25. 1 over 25. Now, please understand, the distribution is 0 and phi, and at 0 the probability is 24 by 25, at here is equal to 1 over 25. So, the probability that x is greater than or equal to phi is in fact 1 over 25, and that is exactly this matches. So, what does it mean? This is exact, and hence there exists distribution for which Markov inequality is tight. So, we gave two examples where one, the Markov inequality is loose, another case is where Markov inequality is tight. If there exists one distribution for which the Markov inequality is tight, that means I can't improve this any further. I can't improve this any further. So, if you are given only, if your assumption is only finite mean, the best you could do is what Markov inequality does, because there exists a distribution that matches the Markov inequality. Now, consider the generalization of that. X is 0 with a probability 1 minus k square, x is equal to k with a probability 1 over k square. Expected value of x by this distribution is 1 over k. Expected value of this distribution is 1 over k. Now, what does it mean? Here is 0, here is k. The probability here is 1 over k square. The probability here is 1 minus 1 over k square. So, k is the largest value the random variable can take, and with the probability 1 over k square. So, if I apply Markov x greater than or equal to k is less than or equal to, by Markov inequality, expected value x given by k, that is 1 over k square, and that is again exact. So, the previous example is a special case of this example, and these two examples essentially show that there exists distribution for which Markov inequality is tight. If something is tight, you can't improve that. I am going to assume again a binomial random variable, a Bernoulli random variable x is equal to 0 with a probability 4 over 8, and x is equal to 1 with a probability 1 over phi. So, here you just say this is 0, this is 1, the probability 1 is 1 over phi, here the probability is 4 over phi, 4 over phi. This is you got the distribution. So, 1 is the largest value it can take. So, the expected value of this is given by this, which is equal to 0.2, which is 1 over phi is p. The variance of that, you can compute this, you can compute that, and if you simplify that, that is equal to pq, that is equal to 4 by 25. Therefore, variance when x is 20, which is equal to npq, which is equal to 20 times 4 by 25, which is 16 by phi. Therefore, by Chebyshev inequality, x greater than or equal to 16, x greater than or equal to 16, please understand, I am still working with the problem, namely it falls here, I am having 20 tosses, I would like to be able to compute the probability that it falls at least 16 heads. So, x is greater than or equal to 16, that is where the 20 comes in. I am considering maximum of 20 tosses, maximum of 20 tosses. So, x when there are 20 tosses, probably a better way of saying that is summation xi is equal to 20, where xi is 1 and 0. That is probably the correct way of saying it. Xi is equal to 20 instead of x is equal to 20. So, probability x is greater than 16 is x minus 4 is greater than or equal to 12. So, I can split that inequality. 4 is the expected value. What is the expected value? The expected value of the 20. So, when there are 20 tosses, what is the expected result of the NPQ? I am sorry, the expected value is the NP, N is 20, P is 1 over 5, so that is equal to 4. So, E of x is 4. So, this inequality can be written x minus 4 greater than or equal to 12, which has the natural interpretation. So, this is essentially the if you put this, it becomes Chebyshev inequality. So, this is less than or equal to the variance of not x, the summation of xi is equal to 20, and that divided by 12 square, that is essentially Chebyshev inequality, and that is equal to, you can readily see, is 1 over 45, and that is equal to 0.02222. So, that is the upper bound coming from Chebyshev inequality. Chebyshev inequality is better than Markov, please understand. For the same problem, the Markov inequality showed an upper bound of 1 over 4. Here the upper bound is 0.022. The actual probability is much less. Therefore, the Chebyshev inequality is less than the Markov inequality. That means the Chebyshev inequality is better than Markov. Now, I am going to talk about the general properties of Chebyshev. Is it the best? Can I improve Chebyshev inequality? So, consider a random variable that takes minus a, plus a and 0 with a probability 1/3, 1/3, this is 1/3, a is greater than 0, expected value of x is 0, the variance of a is 2a square minus 3, these are standard calculations. So, the probability that the absolute value of x is greater than t is less than or equal to variance of x divided by t square. So, variance of x is 2a square by 3 divided by t square. So, that is the upper bound coming from Chebyshev inequality. Chebyshev inequality. So, if I set t is equal to a, if I set t is equal to a, what is a? A is the largest value. A is the largest absolute value the random variable can take, because the random variable can take plus a or minus a. So, by Chebyshev inequality, this is equal to 2a square divided by 3a square, this is 2 by 3. And you do know that it must be 2 by 3. Why? The probability of getting a greater than or equal to a is 1 by 3, probability of getting less than or equal to a is 1 by 3. So, the probability that will the tail 1 by the tail a x minus a absolute value is greater than 0. That's the idea, which is equal to saying that the absolute value of x is greater than or equal to a, that is equal to 2/3, and in this case the Chebyshev inequality is exact. Therefore, Markov and Chebyshev inequality are tight and cannot be improved. Cannot be improved means what? Why cannot be improved? But there exists a distribution for which this inequality gives exact value, even though there exists other distribution for which it is very loose. So, if I want to be able to improve these, I need to look at outside of the framework of Markov and Chebyshev. I need to look at what is called higher moments. So, you can, what is the higher moment? Higher centered moment, x minus mu absolute value to the power k. So, probability that absolute value of x minus mu is greater than or equal to t is the same as probability x minus mu to the power k is greater than or equal to t to the power of k. Applying Markov, this is equal to expected value of x minus mu to the power k by t to the power of k for t greater than or equal to 0. So, what is this? If I know the kth central moment, if I know the kth central moment, we can use the polynomial function of x minus mu to the power k, absolute value of x minus mu to the power k. So, that is a polynomial function of the difference between x and mu. So, we can use, so what does it mean? If I can, this essentially shows that if you want to be able to extend Markov in Chebyshev, we need to look at higher order moments. The higher order moments, so if I can compute higher order moments, I should be able to use Markov inequality and combine it with higher order moments to be able to get polynomial functions. The upper bound could be a polynomial function. So, this is this probability theory, this is probability of the event I am interested. So, this could be a polynomial in the kth central moment. So, that is a line of attack one could use, but computing the kth central moment for different distributions may be challenging. So, one asks the question, why don't you go for the gold? Instead of considering the first moment, second moment, kth moment and so on, why don't you consider the moment generating function itself? Because moment generating function can generate all the moments from 1 to infinity. So, now I am going to define what is called the moment generating function, MGF. It may look like a course in probability theory right now, but please understand, I have already talked about the need for special ways to look at high dimensional probability calculations. So, let x be a random variable, with the moment generating function in the neighborhood of the origin. Moment generating function in the neighborhood of the origin. So, what does this mean? There is a b which is greater than 0, there is an interval lambda, there is an interval 0 to b, that is a non-zero length, interval of non-zero length. I am going to consider real variable lambda in the interval 0 to b. I am now going to define expected value of e to the power of lambda of x minus mu. X minus mu is essentially centering. So, this is the exponential of lambda times x minus mu. Exponential functions are monotonic. So, if x is a random variable, e to the power of lambda x minus mu is a random variable. If you consider that random variable as y, I can apply Markov. According to Markov, what is that I am going to get? The absolute probability that absolute value of x minus mu is greater than or equal to t is given by probability that I am going to take, please understand, I can take the square, I can take the kth power, I can take exponential, and that is what I am doing in here. The inequalities are preserved under monotonic transformation. The events are preserved. This is an event, that is an event. These two events represent the same event. So, the probabilities are same. So, by Markov inequality, this is the random variable. This probability must be less than or equal to expected value of e to the power of lambda x minus mu by e to the power of lambda t. So, this must be true. Look at this now, lambda is a free variable. So, the probability that the absolute value of x minus mu is greater than t means what? Again, this is mu plus t, this is mu minus t, this is the interval I am interested in checking. In order to be able to check this interval, I am going to be look at outside of that, the tail. So, this is the tail event. The probability of the tail event is less than expected value of e to the power of lambda x minus mu by e to the power of lambda t. Now, look at that now. T is a parameter which refers to the tail. Mu is a parameter which refers to the first moment of x. Lambda is a free variable. This inequality must be true for any lambda. So, if this inequality has to be true for any lambda in the interval 0 to b, what is the best upper bound? The smallest upper bound. So, by optimizing with respect to lambda, optimize means with respect to lambda, what is the lambda for which this right hand side will be minimum? because that's the smallest, because I want the upper bound to be small. It is a probability. We all know probability is less than or equal to 1. So 1 is a trivial bound. So I am interested in the optimal bound. I want to be able to optimize the right hand side with respect to lambda in the interval 0 to b. When you optimize this with respect to lambda, you get a new bound called Chernoff bound. That is a very tight bound. It is a better bound because it involves moment generating function. And I also want you to know the definition of a moment generating function. I hope you are all definition, one way of looking at the moment generating function. Phi. I also want you to know sometimes we use phi for the cumulative probability value in Gaussian density. Here I am using phi to represent the moment generating function. So the juncture will tell you which one I am considering. So how am I going to express this? I want, so these, look at this now, this is the probability less than or equal to 1. So if I took the logarithm of a number less than or equal to 1, so I want to be able to show the log of this probability. Look at this now, expectation of the log of the expectation. It can be shown that a tight bound is given by supremum. For those of you who do not know, the word supremum is essentially maximum. The maximum over the interval 0 to lambda, negative of the maximum of this function lambda t minus log of e to the power of lambda x minus lambda times x minus mu. Where is lambda t coming from? This lambda t is coming from taking the logarithm of the denominator. I am going to take the log of the expectation of the numerator. Please understand, the log of a number in less than 1 is negative. I want you to be able to recall the logarithmic curve. This is the logarithmic curve, log to the base e of x. Log of 1 is 0, log of a number in between 0 and 1 is negative, log of 0 is minus infinity, log of a number greater than or equal to 1 is positive. So that is a logarithmic function. So log of a number less than 1 is negative, and the inequality comes in here with a negative sign. So this is negative, this is the negative sign, and that is the expression of the, that is the expression for the upper bound. It can be shown that there are relation between the polynomial bound and the moment generating function based bound, but polynomial bound can be better than moment generating function based bounds, but Chernoff bound in principle is easy analytically to calculate. The polynomial bounds oftentimes are maybe difficult to compute. Sorry. So let me go back and talk about the polynomial bound. So this is the polynomial bound 3. This may be very difficult to compute, but if one succeeds in doing this, sometimes we can get better bounds. But Chernoff bound is much more easy analytically to handle. So from now on we are going to be talking about in this section Chernoff bound. I want to be able to illustrate Chernoff bound by computing the moment generating function for the Gaussian random variable, by computing the moment generating function for the Gaussian random variable. So let x be a general Gaussian random variable with a mean mu and sigma square variance. E to the power of lambda x, expected value of e to the power of lambda x by definition is e to the power of lambda x times the probability density function. This I can add these two together, I get this exponent. Now this exponent, there is a square term, there is a linear term, there is a constant term, there is a linear term, we can combine all the things. So by expressing the exponent as a perfect square and simplifying, and that is a homework for you. please remember, you should be able to complete the square, complete a second degree polynomial, express it as a perfect square plus some correction term, perfect square and correction term, and by expressing this you can readily verify that expected value of e to the power of lambda x is equal to e to the power of mu lambda plus sigma square lambda square by 2. What is mu? Mu is the mean. What is sigma square? The variance of the given random variable. What is lambda? Lambda is the real number for which the moment generating function is defined. In general, the moment generating function may be defined only for a finite interval. You remember in the previous definition we took 0 to b. But in the case of a Gaussian random variable, this is defined for any lambda, this is defined for any lambda, lambda belonging to a real number. Now applying phi, what is phi? The supremum of lambda t minus log of that. I have explicitly calculated the moment generating function from here to here. So if I substitute this is essentially supremum of, supremum is maximum. Supremum is called the greatest lower bound. Infimum is called the largest lower bound. That means if it is x, this is a. If x is less than a, x is less than any number that is greater than a. So what is the least upper bound on x? A. The least upper bound, greatest lower bound. The least upper bound is called supremum. The greatest lower bound is called infimum. Supremum, infimum. So this is going to be supremum of this. Please understand that is the quantity that we have utilized the computation in 6. So this is, I am going to be able to find the maximum value over all real lambda t minus sigma square lambda square by 2, and by taking the derivative and equating the derivative to 0. So I am computing the derivative equivalent to equating to 0. I show this maximum occurs when lambda is equal to t over sigma square. Therefore, the value lambda, the maximum value lambda is t square by 2 sigma square. So from here you can readily see by phi, what is phi? Please go back. The basic inequality is phi. So the log of this probability less than minus of the supremum. The minus sign comes because of the negative, I am sorry, the log of a number less than 1 is negative. Therefore, you get the first bound. This is the upper inequality. That means x greater than mu plus t. That means if I have mu, this is mu plus t, what is the probability that x will be greater than mu plus t? That is e to the power of minus t square by sigma square. Oh, that is a very nice exponential bound. This bound decreases at the square of t. So this bound is sharper. It can be shown this bound is sharper up to a polynomial factor. You don't have to worry about the polynomial factor if you are not concerned about this, but that's a very nice bound. Tail bounds obtained using Chernow method depends on the growth rate of moment generating function. So the moment generating function for the Gaussian random variable is given by this. This is the moment generating function for the Gaussian random variable. So the moment generating function depends on the growth rate of the moment generating functions, and that's what explicitly being used in here. So, what is the Chernoff bound? Chernoff bound is going to give you the probability that it is going to be larger than t. In the case of Markov, I simply got e by t. In the case of Chebyshev, we got variance of x by t square. Now, I am going to get it, the upper bound is going to be e to the power of minus t square by 2 sigma square. Now, please understand, 1 over t goes to 0 as t becomes larger. 1 over t square goes to 0 faster than 1 over t. E to the power of minus t square goes to 0 even faster than 1 over t square. I think that's the thing you need to be able to appreciate in here, because the random variable has a fixed mean, has a fixed variance. So, the Markov inequality, the bound goes to 0 as 1 over t. Chebyshev inequality goes to 0 as 1 over t square. The Chernoff bound goes to 0 as e to the power of minus t square by 2 sigma square, and you should by now know that the exponential function I increases faster as well as decreases faster compared to polynomial functions. With that in mind, now I am going to extend the notion to what is called the sub-Gaussian random variables. So, let us see where we are right now. We wanted to be able to study the tail distribution. We introduced Markov, we improved it by Chebyshev. Then we said we could further improve it by using kth moment, which is the polynomial in x minus mu to the power k. Computing the kth moment could be challenging. We have already illustrated the difficulty of computing the third moment, fourth moment for Gaussian random variable in the module on Gaussian distribution. So, you now know the mathematics of it, but it turns out computing the moment generating function could be simpler. We wanted to illustrate this by using Gaussian random variables. So, what is the basic property of the Gaussian random variable? The basic property of the Gaussian random variable is that there are two things: expected value of e to the power of lambda x is equal to that, and the probability that x greater than or equal to mu plus t is less than or equal to minus t square by 2 sigma square. So, mathematicians are interested in generalizing this. So, they introduce the concept of what is called sub-Gaussian random variable. I am going to give a definition. A random variable x with a mean mu is called a sub-Gaussian SG if there exists a constant a and a sigma greater, if there exists a sigma greater than 0. What is sigma? The variance. It denotes the variance. It denotes the standard deviation. Sigma square is the variance. So that for all lambda belonging to R, e to the power of lambda x minus mu is less than or equal to e to the power of sigma square lambda square by 2. So, lambda times e to the power of lambda x, you have the mu lambda, but if you consider e to the power of e to the power of lambda times x minus mu, this term cancels. So, exponential of e to the power of lambda times x minus mu is simply exponential of sigma square lambda square by 2. If it is equal, it is Gaussian. Now, what is that we say? It is sub-Gaussian if x is a random variable with a mean mu. This is the moment generating function. The moment generating function is less than or equal to e to the power of sigma square lambda square by 2, and this is the bound that I get from the moment generating function for the Gaussian random variable. If it is equal, it is Gaussian. If it is less than or equal, it is called sub-Gaussian. We say sigma greater than 0 is called a sub-Gaussian parameter. Please understand, sub-Gaussian refers to a distribution. We are not trying to give a formula for the distribution. We are going to give a description of the distribution through the expected value. Your random variable x is said to be sub-Gaussian if expected value of lambda times x minus mu is less than or equal to e to the power of sigma square lambda square by 2. Now, if sigma is called the sub-Gaussian parameter, is always positive. Now, from here you can readily see if x is a normal random variable with mean mu and sigma square as the variance, then it is clearly sub-Gaussian. So, every Gaussian is sub-Gaussian, but there exists sub-Gaussian that are not Gaussian. So, this is an extension of the notion of Gaussian distribution into sub-Gaussian. Now, we only talked about x is greater than mu plus t. By symmetry, I can consider minus x. So, now we can say that if x is Gaussian, minus x is also, if x is Gaussian, minus x is Gaussian. If x is sub-Gaussian, minus x is also sub-Gaussian. Therefore, by symmetry, minus x is sub-Gaussian if x is. Thus, we get a lower deviation inequality. What is the lower deviation inequality? Here is mu plus t, here is mu minus t. This is called the upper deviation, this is called the lower deviation. Thus far, we considered upper deviation x minus mu greater than or equal to t. We can also now consider x minus mu absolute value is greater than or equal to t. If you say x minus mu greater than or equal to t, that is only the upper. If you say absolute value of x minus mu greater than or equal to t, this is upper and lower. Upper and lower. So, by combining the two, if x is Gaussian, minus x is also Gaussian. If x is sub-Gaussian, minus x is also sub-Gaussian. So, for any sub-Gaussian random variable, we get the concentration inequality. And what is the concentration inequality? The probability that x minus mu is greater than or equal to t is less than or equal to the probability that lies in here plus the probability lies in here. The probability that lies in here is less than or equal to e to the power of minus t square by is minus t square by 2 sigma square. So, this is the definition of a tail bound for sub-Gaussian random variables. So, Markov, Chebyshev, Chernoff, Chebyshev for Gaussian, properties of Gaussian, generalization of Gaussian to sub-Gaussian. If x is sub-Gaussian, minus x is sub-Gaussian. So, if there is an upper limit, if there is an upper deviation, there is a lower deviation. These two are mutually exclusive. So, the probability that absolute value of x minus mu is greater than or equal to t is twice the probability of individual events, which is minus t square by 2 sigma square. I hope you are all with me now. I hope you are all with me now. And these are all generalizations of 9. These are all generalizations that coming out of, sorry. Yeah. So, 7 is the upper inequality. By using symmetry, x replacing x by minus x, I get the lower inequality. By combining the upper and lower inequality, I get 9 out of 7. So, now what is that we are going to be doing? We are going to be concentrating on sub-Gaussian random variables. Sub-Gaussian random variables have a very beautiful expression for the tail probability. So, this is the tail probability. This tail probability is decreasing as a function of t, and this decrease is e to the power of minus t square. That means the tail probability becomes smaller and smaller as t becomes larger and larger, and t is a real random variable. So, this is a very important tail probability, and controlling the tail is equal to concentration. Please understand, if the tail probability is small, then it is concentrated around some interval around the mean. So, that is what the whole idea is. If this is mu, if this is mu plus t, if this is mu minus t, if to show that the probability that in this interval is large is to show the probability outside of this interval is small, and is small exponentially e to the power of minus t square by 2 sigma square. So, that is the large family of random variables which are called sub-Gaussian. Again, I want you to understand that sub-Gaussian, we are not going to describe the distribution itself, but we are trying to describe the tail, is defined by the tail probability. Now, I am going to give you examples of sub-Gaussian random variables. So, I have already shown Gaussian is sub-Gaussian. So, let us be a random variable such that p of x is equal to 1, p of x is equal to minus 1 is half. That means it is a symmetric random variable, Bernoulli distribution, symmetric random variable plus 1 minus 1 half half. Such a random variable is called Rademacher random variables. Sometimes we call it Bernoulli, sometimes we call it Rademacher. Here is a specific thing. In Bernoulli, I can assume 0, 1 or 1 minus 1. But Rademacher random variable is always minus 1 plus 1 and taking equal probability half half. Now, go back. If x is a random variable, the moment generating function is equal to expected value of e to the power of lambda x for some lambda in some finite interval, finite or infinite interval, e to the power of lambda x. That is a definition of moment generating function. So, I have a random variable, I can compute this moment generating function. The moment generating function is 1/2 of e to the power of lambda plus e to the power of minus lambda. I am going to express this as a series in lambda, as a series in lambda. These are the two series expression. Here alternate terms are positive and negative, here every term is positive. The negative term and the positive term cancel, leaving behind only the even powers. So, this is given by the infinite sum, k is equal to 0 to infinity lambda to the power 2k by 2k factorial. So, the denominator is 2k factorial, 2k factorial is greater than 2 to the power of k times factorial. So, if I change the denominator by a smaller number, the value of the fraction increases. So, the equality becomes inequality. So, this is 1 plus k is equal to 1 to infinity lambda to the power 2k divided by 2 to the power of k lambda k factorial, and this can be readily seen to be equal to e to the power of the whole thing can be easily seen to be equal to e to the power of minus lambda square by 2. Please understand this whole sum. So, I had exact inequality. I have exact equality, I created an inequality by deflating the denominator. If I deflate the denominator, the value of the fraction goes up. Therefore, 2 to the power of k times k factorial is less than 2k factorial, and because of that I get this inequality e to the power of lambda square by 2. So, that means the moment generating function for the Rademacher random variable is e to the power of lambda square by 2. So, this essentially tells you the moment generating function is less than e to the power of minus lambda square. That means it is a sub-Gaussian random variable. Go back, when is a sub-Gaussian random variable? An inequality of this type holds good. So, that is exactly what is given in here. This e to the power of lambda x is less than or equal to e to the power of lambda square by 2. Therefore, x is a sub-Gaussian random variable with the parameter sigma is equal to 1. Please understand, sigma is the parameter for the sub-Gaussian random variable. Any bounded random variable is sub-Gaussian. So, let x be a bounded random variable xt in the interval a b with 0 mean. If x is 0 mean in the interval a to b means a must be negative, b must be positive. Let y be a copy of x, which is the independent copy of x. So, e to the power of x, e to the power of lambda x, expected value of e to the power of lambda x with x, that can be written as, because x and y are two independent copies, x and y are two independent copies and they are 0 mean. So, mean of y is also 0. So, mean of y is 0. So, x is x minus e of y because this is 0. So, these two are equal, e to the power of lambda x minus e y of y. Now, y has a distribution, x has a distribution, both are identical. So, this is equal to e to the power of lambda x minus y, where I am going to integrate it with respect to x and y independently. So, y is the identical copy of x, independent identical copy of x, that is why we are able to do this. This kind of argument is called symmetrization. It follows from convexity of exponential functions and Jensen's inequality. What does the convexity function means? A function is said to be convex. This is x, this is y, this is x, this is y, this is f of x, this is f of y, this point is z, z is equal to alpha x plus 1 minus alpha times y. That is any point in the interval 0 to y can be obtained by alpha x plus 1 minus alpha times alpha x plus 1 minus alpha times y. That means z is equal to alpha times x plus 1 minus alpha times y. Now, this is f of z. So, this is the point z, this is the point f of z, this is the point above f of z. So, what is this value? This value is essentially alpha times f of x plus 1 minus alpha times f of y. So, what does this say? F of alpha times f of x plus 1 minus alpha times f of y is greater than or equal to, the point on the top is greater than or equal to f of alpha x plus 1 minus alpha y. This inequality is called convex inequality. Any function that satisfies this for every pair of point x and y is called convex functions. So, what is the colloquial way of looking at the convex function? If you join this point is x f of x, this point is y f of y, this is the chord joining the 2 points, the function is always below the chord. So, there is a chord, there is a function below the chord. Such functions are called convex functions. Y is equal to x square, the parabolic function is a convex function. So, this is the inequality. This inequality is called convex inequality, that is essentially this inequality. So, if f is convex for any point x1, x2, this must be true. So, what is this? You can think of this as alpha is a probability, 1 minus alpha is the complement of the probability. So, this you can think of this as E of x, you can think of this as E of f of x. So, E of f of x, f of E of x, f of E of x is less than or equal to E of f of x. So, this inequality holds good for any convex function. Exponential functions are convex functions, x square is a convex function. Therefore, according to this inequality, e to the power of lambda x minus e of y must be equal to expected value of y with respect to lambda x minus y, expected value of, that means I am just considering x fixed, y is a variable, and the distribution of y is identical to that of f, and E y of y is essentially expected value of y, expected value coming from the same distribution that x and y share. So, that is the equation 12, inequality 12. Let z be an independent Rademacher variable. Now, we all know what a Rademacher variable is plus or minus 1 with the probability half half. Then the distribution of x minus y is the same as z times x minus y. Z times x minus y. So please understand, this is again called the symmetrization argument. If z is an independent Rademacher random variable, x is a variable, y is an identical copy of that. So I am considering bounded random variables, I am considering the symmetrization argument, I am using convexity property. Now I am considering the x and y are two bounded random variables, x minus y is a bounded random variable. If z is an independent Rademacher variable, it can be verified that the distribution of x minus y is the same as the distribution of z times x minus y. Z times x minus y. This is called symmetrization argument. From this symmetrization argument, expected value of x and y of e to the power of lambda x minus y is equal to expected value conditioned on z. So z is given, e of z of this is equal to expected value of x of the same expectation as on the left hand side. But we do know the expected value of z on this side is lambda square x minus y whole square by 2. So we have already alluded to this in the earlier argument. So this is equal to expected value of x comma y of e to the power of lambda square x minus y whole square divided by 2. Where so what is that we are trying to do? We are keeping x and y fixed, and we use 10 to where lambda is replaced by lambda times x minus y. Let's go back to 10. I just want to be able to, oh I am sorry, 10. That is the equation 10. The equation 10 relates to the property of the Rademacher random variable. So using 10 I can compute this one as, so if I keep x and y fixed, it is a random variable z, which is a Rademacher random variable, and I already know the moment generating function of the Rademacher random variable from 10. So this is less than or equal to expected value of that, where we keep x and y fixed and use 10 where lambda is replaced by lambda times x minus y. I hope you are all with me. And this inequality comes from using the properties of moment generating functions. This property comes from the fact z is a sub-Gaussian random variable. So from here to here the equality becomes inequality largely because x and y are fixed, z is a bounded random variable which is Rademacher random variable which is sub-Gaussian. So I am again using the sub-Gaussian property of Rademacher random variable. So now recall x minus y absolute value is less than b minus a. So we get expected value of the e to the power of lambda square x minus y whole square divided by 2 with respect to x and y is less than or equal to e to the power of lambda square b minus a whole square by 2. Therefore x is SG. SG means what? Sub-Gaussian with the parameter sigma is equal to b minus a. So we are trying to extend the notion and give examples of the concept of sub-Gaussian. Gaussian is sub-Gaussian. Rademacher random variable is sub-Gaussian. Bounded random variables are sub-Gaussian. That we used a trick called symmetrization. It's a very nice probability trick. I think you must get used to using such tricks. Now another property of sub-Gaussian is that if x1 and x2 are two independent sub-Gaussian random variables with the parameter sigma 1 square and sigma 2 square, then x1 plus x2 is sub-Gaussian with the parameter sigma 1 square plus sigma 2 square. That's a homework problem. That's a homework problem. That means, please understand, sigma square we interpret it as a variance for Gaussian. Sigma 1 and sigma 2 we interpret this as parameters for sub-Gaussian. Of course, for Gaussian sigma square the variance is a parameter. So, what is that we have accomplished now? We have seen Markov, we have seen Chebyshev, we have seen Chernoff, we have seen moment generating function. We talked about the properties of moment generating function for Gaussian random variable. We generalized, we took off from there and defined what is called sub-Gaussian random variable. So, Gaussian is sub-Gaussian, Rademacher variable is a sub-Gaussian, any finite random variable is sub-Gaussian, and we have also now claimed that if x1 and x2 are two independent sub-Gaussian random variables with the parameters sigma 1 and sigma 2, then x1 plus x2 is also sub-Gaussian with the parameters sigma 1 square plus sigma 2 square. In other words, if you add the two independent sub-Gaussian random variables, their parameters also get added. So, it is a nice exercise. You have to manipulate the moment generating function with a little bit of algebra, you should be able to do that. Now, from Chernoff, from sub-Gaussian, we are now going to go to Hofding inequality. Please understand, the reason we are trying to do these things is because these are tools that are needed to be able to quantify the tail probability. If I can show the tail probability is small, then the measures are concentrated. The topic is measure concentration. We already talked about distance concentration, measure concentration, and so on as a prelude in the previous modules. So, what is the Hofding inequality? It relates to sums of independent sub-Gaussian random variables. So, it builds on sub-Gaussian theory. So, let xi be independent random variables with mean mu I and are sub-Gaussian with parameters sigma I. That means, x1, x2, x3 are independent random variables, each of which is sub-Gaussian. The mu, the mean may vary, so they are not identically distributed. The mean different means the distributions are different, and the sub-Gaussian parameters are sigma I is equal to 1 to n. That means the parameters also different. So, I am considering a set of n random variables potentially from n distinct distributions with distinct mean and distinct parameters, sub-Gaussian parameters. Then for all t from the basic properties of the sub-Gaussian, please understand, the sum of Gaussian is sum of sub-Gaussian is sub-Gaussian so long as they are independent. So, these are independent. So, this is the sum of centered sub-Gaussian random variable I is equal to 1 to n. So, I am interested in finding when will the sum of the difference between the random variable and their respective mean is greater than or equal to t. So, it is a kind of a complicated tail bound. This complicated tail bound, by virtue of the theorem that we have seen, what is the theorem, the homework problem we have seen? If x1, x2 are sub-Gaussian with parameters sigma 1 square, sigma 2 square, their sum is sub-Gaussian with the parameter sigma 1 square plus sigma 2 square. So, by applying that theorem, I simply get 15. So, this tail is essentially follows from the claim that sum of sub-Gaussian is sub-Gaussian if so long as they are independent. This is often stated as a special case of bounded random variables. So, if all the random variables, I simply assume the random variables are independent and having a mean mu I. Now, I am going to assume all the random variables are in the same interval a to b, they are bounded. Then a special version of that is probability that this event happens. The probability that this event happens is less than or equal to minus t square by 2n times b minus a whole square. b minus a whole square. Please understand that the sigma i's are parameters. Here the parameter sigma I is replaced by b minus a. So, b minus a square is the bound on each of the sigma I. There are n such sigma I square. So, that becomes n times b minus a whole square, n times sigma I whole square. So, this gives rise to what is called an equivalent characterization of sub-Gaussian random variables. This is the theorem. This theorem is given in chapter 2 of Wainwright's book, which I already talked about. Let x be a 0 mean random variable, then the following things are equivalent. This is a complete characterization of sub-Gaussian random variable. Please understand, we are not trying to describe a random variable by the distribution, but we are trying to describe the probability density function through inequalities. Inequalities on moment generating function, inequalities on tail bounds. So, if there exists a sigma greater than 0 such that the moment generating function is less than e to the power of minus lambda square by lambda square sigma square by 2. So, this is the starting definition. Then it can be shown in mathematics. We always want to be able to see different ways of describing the same property. So, property 2 and 3 are equivalent to property 1, and what does it say? There exists a c constant greater than 1, and there is a normal random variable with mean 0 and r square as the variance. Then the probability that x greater than or equal to s is equivalent to probability c times the probability absolute value of z is greater than or equal to s, and this probability will depend on r square, as you already know. And the third form would be to give examples of all moments, even moments. So, for k is equal to 1, 2, etc., expected value of e to the power of 2k. So, expected value of x square, x to the power of 4, x to the power of 6, and so on. So, all the even moments are given by 2k factorial divided by 2 to the power of k times k factorial. We have already met this quantity earlier. I am not going to prove the theorem. The theorem is proved in chapter 2 of that book, and these are equivalent ways of describing sub-Gaussian. The reason why we are going to be talking about sub-Gaussian in here is because we are going to be deriving an important result in dimension reduction in the context of big data variable using the properties of sub-Gaussian and sub-exponential function. So, sub-exponential is something to come. So, note that 1 is the definition of sub-Gaussian, 2 follows from sub-Gaussian dominated by G, and 3 gives control over the moments. And the fourth one is, this is the moment generating function. We can always show that this is less than or equal to 1 over square root over minus lambda for lambda in the interval closed open interval 0 to 1. This is a slightly advanced result, but it is good to know this result.